and it is a elastic collision. I'm gonna probably, I don't know whether this one recoils off of it or not. I won't know until after I work the numbers. But this one is probably going to go in that direction. I'll call that V2. This is the 22 gram, and this is the 44 gram. Momentum is conserved, but that doesn't give us enough information to solve the problem. Conservation momentum will give us 44 times 2.3 plus 22 times 0. But after the collision, we'll have 44 V1 plus 22 V2. When you're doing these problems, I would highly encourage you not to put any explicit negative sign in front of an unknown velocity. If it's going to be negative, it'll work out in the problem. Now, if they tell you the velocity is v for the first object and negative v for the second object, you will have to put that explicit in there because they're explicitly telling you it's negative. But for an unknown, a non-given velocity, don't assume negative or positive. It just makes it more confusing later. So just put V1 and V2 in there. This is not enough to solve the problem, but I will point out, I put the masses in, but the very first thing I'm going to do is divide out by 22. Now I would do this even if they weren't the same. If they were different, I would try and get the lead coefficients to be as low a number as possible. I am eventually going to have to isolate V2 or V1 by itself. So I'm anticipating I'm going to have to do that eventually. So I'm dividing the entire thing by 22, which is going to give me 2V1 plus V2 equals 4.6. Any questions? All right, that is not enough information to solve the problem. But they told me it's elastic, so 1/2 mv squared plus, I'm not even gonna do this one, it's 0, equals 1/2 mv squared plus 1/2 mv squared. It's my second piece of information. Now there's some obvious things that you can do here, and I know that you guys, if you attempted this, you know already all these 1/2s are going to go away. I'm still going to divide by 22. It's going to reduce it down a little bit so that I'll get something a little easier to work with. I'm going to have 2v1 squared plus v2 squared equals, now I'm sorry, but 2.3 squared, I don't know what that is. Thank you. Give everybody a minute to catch up with you. All right, go ahead. 5.29. Then I have to multiply by 2. So 10.58. Now, I have 2 equations and 2 unknowns. This is my first one. This is my second one. There is no easy way to do this. At least none that I've found in the years I've been teaching. You're stuck with having to figure this out. Now you have at least one helpful method that I'll point out later, but I'll be honest, you're just going to have to brute force it. I am going to get to another page here, so I have a little more space for this. So V1 has 2 values. The value before the collision and the value after the collision. This is one of our answers already. It's not like there's some random possible answer here. We asked the problem, the mathematics, to tell us the 2 velocities the object could have before the collision and the 2 velocities it could have after the collision, so that momentum would be conserved and energy would be conserved. So the 2.3 is one of our answers. Got this problem now for all. I'm going to take and solve for the V2, which is going to be 4.6 minus V1. Then I have the 10.58 equals 2V1 squared plus V2 squared. So I'm going to square this so I can, use it on the other side. I'm going to have to do substitution. So 4.6 squared, again, that's kind of beyond me. So I don't know what it is. I think it's 21.16, but I'm not sure. Is it? What?
Wasn't it 2v1 on the left side? Or am I remembering it wrong?
I don't remember. Is it 2v1 on the left side?
I thought it was.
Okay.
It was 44.
Okay. Better?
I believe so.
Oh, great. So, still 21.16 here when you square it? Square 4.6, is that right? All right. Then I'll have my cross term, which is going to be, let's see, it's 9.2 doubled, 18.4. Am I the only one doing it? I need the cross term. You guys know how to do a binomial. It's 2 times 4.6, then double it.
You're right.
What is it?
18.4.
I'm going to have to stop guessing the answers so that you guys have something to do. Plus 4v1 squared, but I'm running out of space here, so I'll have to erase the line. Plus 4v1 squared. There we go. All right, so now I have to put all of that where v2 squared is. So 10.58 equals 2v1 squared plus 21.16 minus 18.4v1 plus 4v1 squared. Yikes. Nothing pleasant about that, is there? So, got to clean it up and turn it into a quadratic. So, I'm going to just do a little addition and subtraction here. I'm going to get, I don't know, let's do the 2v1 squared and the 4v1 squared and get 6v1 squared. And there's only one term with v1 in it, so minus 18.4 v1. And then I have to move this to the other side, so 21.16 minus 10.58. I'm pretty sure that's just 10.58.
Yeah.
So that'll be plus 10.58 equals 0. Now, I know that you would want to jump right to the quadratic formula. Can I encourage you not to? We actually know one of the answers for V1. And for all of you who have already stopped paying attention and are lost, perhaps perk up now. These look complicated because they are mathematically complicated. But it's a quadratic. And because it's a quadratic, it has to produce two answers. So we know that we're going to use a quadratic function that's going to have a plus or minus in it. It's going to give us two answers. And you're used to, when we have these things, throwing away one of the answers. Or perhaps not using one of the answers. But that's not the case here. We already know one of the answers. Which means you can always factor. It will make it faster. One of our answers has to be 2.3. Now, unfortunately, there's a 6 out here in the front. So if you want to use the method I'm about to outline, you should divide every one of these terms by 6. It'll make it easier to factor. If you don't want to do it this way, then don't. Negative b plus or minus the square root of b squared minus 4ac divided by 2a will give you both of your factors too. I'm just pointing out that we know that one of the answers has to be 2.3. If we had solved for v2, one of the answers would have been 0. It would have actually been easier to solve for v2. Now, I'm going to take a break because if you want to see this problem to the end, you're going to either need to use the quadratic formula or you're going to have to factor, and I'm not going to do it. I'm going to let you guys do it because this is math and it's not physics.
Yep.
Go ahead.
Do you want it in decimals or fractions?
Whatever. So what is the other v1?
23 over 30.
23 over 30?
I got 23 over 30 and 23 over 10.
Well, 23 over 10 we know is 2.3, so I have confidence that 23 over 30 sounds right. So that's, I don't know what it is. I'll just leave it as 23 over 30. Let's pick this one to figure out what V2 must, no, not that one. What am I doing? That'd be stupid. We'll pick V2 equals 4.6 minus 2V1 to figure out V2. So 46 divided by 30. You're gonna have to get a decimal on this. I'm not doing it. It's making my head hurt just thinking about it.
3.06.
What is it?
3.06.
Okie doke. I'm gonna believe Jake. Why not? And 23 divided by 30. Do we have a decimal on that one for me? 0.77. Fantastic. Those look to be my two answers. Now, we know yours are different because they scrambled the numbers on you, right? But this is the process that you go by to do this. Look, it's long. Just with the pause in place, I've been talking 10 minutes. How likely can you do this on the AP exam?
Not likely.
Yes, ma'am?
In the textbook, they have formulas written out for like V1 and V2, depending on like which object is at rest. Would it be like worth memorizing those?
No. No, yeah, obviously if one's at rest, there's going to be a formula that you can plug in and solve and eventually get it. I've seen elastic collision questions on the exam. They've existed. But it's so few and far between. Most of the time, if they're going to have an elastic collision, it's going to be done in such a way that either the numbers work out really fast. Like you can make choices here for the numbers that work out really easily. You make multiples of masses and you choose numbers that just work out. In which case the math actually falls together pretty fast. Also, they're more likely to ask if it's an elastic collision and have you verify it since it teaches the same or it asks the same information from you without it being so math heavy. Does that make sense? So they might just give you one of these, ask you to figure out the other one, and then ask if it's an elastic collision. Does that make sense? That is the most likely way elastic collisions would be tested on the exam, is verification rather than prediction. Is there more to this question you want me to go over?
No,
All right.
I got the second part right.
All right. Let's try something else. Yep.
20.
Which one did you want to see, Jackson?
I don't have the number. I have like the problem number 11.41.
Okay, so. Sorry, the internet just went out real quick, so I had to wait for it to boot back up. All right, so we're going to do 20 first, and then we'll do 11 point, what'd you say?
41.
That is number 20.
Oh, okay.
How convenient. All right, an 180 gram ball is dropped from a height of 1.7 meters. Your numbers may vary. Bounces on a hard floor and rebounds to a height of 1 meter. The figure shows the impulse received from the floor. What maximum force does the floor exert on the ball? Let's take a quick dive down this graph real quick, just so that you have this. So in this problem, there is a graph of the impulse. And it's not really a graph of the impulse, it's a graph of the force. So they have, what is that? F max here. And the graph is just a little triangle. And they tell us that this is, I have 5 milliseconds on mine.
I think that one was the same for all the questions.
Okay. It says what maximum force does the floor exert on the floor. Here's how you have to do this problem, because we can figure out the impulse on the ball. That we can figure out. The ball was dropped from 1.7 meters. That's the number I have. I don't know what number you have, but you're going to use something similar. So the ball was dropped somewhere above the ground. So here's the ball dropped. And I have 1.7 meters. You use your number. But it bounces back up only to 1 meter. Now, directly from this, I can't figure out the impulse. I need to know what the change in momentum was to figure out the impulse. To figure out the change in momentum, I will need to know how fast the ball was traveling just before it struck the ground, and then how fast it was traveling to recoil. Now that you can do pretty straightforward, like if you use conservation of energy. But in both cases, you would find it by getting V equals the square root of 2GH. Hopefully you guys have gotten to a point where you've memorized this. That will make these problems a lot faster, and this kind of stuff shows up all over the exam, so it's worth memorizing. So I have the square root of 34 and the square root of 20. So I know this one is 4.4 meters per second, because that's the square root of 20. I don't know what the square root of 34 is. It's a little less than 6, a little more than 5. So like 5.8 probably.
Yeah, it would be 5.8.
So 5.8 meters per second. So those are my two velocities. I'm going to work from those. The impulse is the change in momentum. Somebody throw out whether upwards is positive or upwards is negative.
Upwards is negative.
All right, if upwards is negative, then the final momentum will be 0.18 times negative 4.4 minus 0.18 times 5.8. 4.4 and 5.8 is going to be 10.2. I don't know. 1.9. I don't know what you get. I need the impulse here before you go on. It's negative.
Negative 1.836.
1.836. That's going to be Newton seconds or kilograms meters per second. And the units are the same. This is the impulse on the ball. Now, here's where it's going to get a little dicey. This equals the integral of f dot dt. I can't put f times time because the force wasn't constant. And I'm not actually going to do this integral, but I am going to use this integral to recognize that this area also represents the impulse. Is that pretty clear? And you should know that already from our discussions. But that area is the impulse, which means that since it's a triangle, that's going to be 1/2 F max times 0.005. That's the area of a triangle, right? 1/2 base times height, with the base being 5 milliseconds. That's 5 times 10 to the negative third. And that has to equal this area. The negative sign just means the force is upwards. Is that okay? Is there more to this question? This is quite enough, I think, but using your numbers will probably help there. All right. If that's okay with you guys, then I'll move on to another question. All righty. Do you have a question about this one, Jake, or another problem? Anybody besides Jake? All right, Jake.
Can you do number 22?
Yeah, I sure can.
I think it's we were able to find the answer for the second part, but we couldn't figure out how to derive the equation for the first part.
Okay. A bullet of mass M is fired into a block of mass big M that is at rest. The block with the bullet embedded slides. The block with the bullet embedded slides distance d across a horizontal surface. Okay. Coefficient of kinetic friction is mu k. Okay. I'm seeing two parts to this question. So let's see if you guys see it as well. I see a collision portion of this problem where the bullet and the block are separate entities and the block isn't moving and the bullet is. So that's the start of the problem. I see a transitional part where the bullet strikes the block and the system will have a combined velocity after the collision. And then I see this system sliding across the ground until it reaches a place where the velocity is 0 And we know that it slid a distance d during that time. Do you guys see all those components? Do you have any question about what I've outlined here? Look, this is the stuff that's on your exam. These kinds of problems. Momentum is conserved during the collision, but only during the collision, which means the instantaneous moment before the bullet struck the block and the instantaneous moment after the bullet became embedded. During those two moments, the momentum of the bullet had to be equal to the momentum of the bullet and block together. I don't know why I put a V inside the parentheses there. I guess I'm just disturbed about the grade thing I found out earlier, and I'm looking around at people, and I don't think they're taking this seriously enough. But this is where I start. Now, the thing about this is that after the collision, the energy is taken away from the system by friction. Now, there's a number of ways we can deal with this transition. I would probably look at the work-energy theorem, because the work-energy theorem tells me that the work done by friction is going to equal the change in kinetic energy of the system. I kind of like that method. But you don't have to do it that way. You could use a motion equation and Newton's second law. Take your pick. It really doesn't matter. So I'm going to use the work-energy theorem because it just combines everything into one equation. But motion equation and net force will do the same thing. In order to do this, though, I do have to realize that while the box was sliding, it was experiencing a frictional force in this direction while it moved to the right. And that frictional force equals mu times the normal force, which is going to be mu m plus m times g. That's the frictional force. Any question about that? Yep. You have a question about that, Jake? Okay. So that's going to be work done by friction. Frictional force times distance times cosine of 180 degrees. The three parts of doing work. And that has to equal 1/2 m times 0 squared minus, and I'll put the whole thing here, 1/2 m plus m vt squared. I just put the one little m there because I'm running out of space on my little tablet here to fit it all in. But this should have been both m's. But I know it's 0 because at the end, the thing stopped moving. That's a change in kinetic energy. So ultimately, I get mu m plus m g d cosine 180 equals negative 1/2 m plus m vt squared. Well, it sure looks like. Now, I don't even know what I was supposed to solve for, I'll be honest with you. I just put all the pieces together that I was given. What are we actually supposed to find?
Bullet's velocity.
Bullet's velocity? So I assume then v in terms of everything else. Big M, little m, g, mu, d. All right. So it looks like I only have one invented variable here. What's the invented variable that I put in that wasn't given to me? No. I'm always allowed to use physical constants. There is a variable there that I had to create that I'm not allowed to have in a problem. That's right, VT. I created VT. It can't be in the answer, so I need to eliminate VT. So it looks like I can eliminate it in the energy equation and plug it into the other one. So that's what I'm going to do. First, cancel out this and cancel out this. So VT equals 2 mu g d, and I take the square root. Yay?
There was a lot more to that, wasn't there? No.
Nope, doesn't look like it. So plugging it all in, I'll get mv equals m plus big M times the square root of 2 mu g d. So I have to divide both sides by little m. There it is. No, there's nothing else to this problem. But that's a lot. So I'm not going to say that's small potatoes. That's a lot. But no, there's nothing else to this question after this. Well, I mean, there might be a part B. I don't know.
Yeah, and I
Yeah,
was
let's
just
just
plugging
keep
in,
plugging in those numbers.
Okay.
which is crazy because I got the right answer for that, but I did not use that formula.
Me too.
Oh. What'd you do?
I honestly have no idea. It was like 11 o'clock and I was just doing things and I got the right answer.
Okay.
Couldn't do that.
Look, do not count on numbers tomorrow. I'm thinking this is what you should expect to be able to do.
Yeah, see, I'm sure I could. I really would have thought about it.
Just a quick question. I mean, that's what I'm expecting you guys to be able to do on an FRQ. It's this here is friction, or it swings upward and converts the energy to gravitational potential, or it compresses a spring. They're all the same question, right? There's going to be the collision part somewhere in the problem. And then after that, there's going to be something else. I was talking to another class about a problem I really like. So this one's, like I said, this one's a little different. They take the energy out of the system using friction. This was not in the homework, but this is one I really like. And it's this one that has and if you watch the video that I did for fourth period, you know that I did this problem in fourth period. I did a different problem in your period. I did a ballistic pendulum in your class. And I did this problem in fourth period. I would look at it. In fourth period, it was a spring. In this class, I'm using a ramp. But they're the same question. If you have a frictionless surface, and I have a little block here that's going towards the ramp. If the ramp isn't fastened in place, if it can slide, when the box makes it up to the ramp, it's going to start to go up the ramp. But as it does, the ramp's going to start to move. I would really encourage you to watch the other video. In the other video, there's a similar question that I went through all the way, and that is a box that is moving towards another box with a spring attached to it. These are the same question. There's several different outcomes, though, that can occur in this question. There's the instance after the block touches the spring where the two boxes will have at one moment the same velocity. And they'll both be moving together. It's only for an instant, because as that spring compresses, it starts to push the other box so that the other box starts to move. But they will eventually reach this point where they have the same velocity. That's an interesting point, because the point where they have the same velocity is the point where the spring is at max compression. Now, the reason that's important is because momentum and energy are conserved. The system has kinetic energy with the first block. When the first block and the second block are both moving at the same speed, we have kinetic energy because they're both moving at whatever this new speed is. But there's also energy tied up in the spring now. Those have to be equal. Eventually, further along, the boxes will separate. And this problem is just like an elastic collision, since all the energy can be traced and mechanical energy is conserved. During all of this time, momentum is conserved. So I have mv here plus 0, and I'll have m plus m times vt here, and then I'll have, mv1 here plus mv2 here. Now, Jake, you had your hand up?
Yeah. You said that they're the same kind of question for both. Would you just, instead of the 1/2 kx squared, would it just be mgh for
Yep.
the ramp at the top?
That's exactly it. That's why it's a neat question, because a lot of students don't think to do that. But if the box is moving here and it hits that ramp, there's going to become a time where the box reaches its maximum height along the ramp, but both of them have the same velocity. The potential energies in this box. So there's mgh for the box plus 1/2 m plus m v squared for the box and ramp because they're moving sideways. Before that was just 1/2 mv squared for the box. These have to be equal because energy is conserved. We don't stop thinking about energy conservation just because our system has a collision. These collisions can still conserve energy, even if they don't conserve kinetic energy. That's the important distinction, is that an elastic collision conserves kinetic energy, but collisions can still conserve energy. They just transform it to different types. Both of these problems have been on the AP exam, and they're prevalent. So mathematically, it's interesting. The final case, though, the thing that I do want to kind of throw in front of you, and the reason I brought it up, even though it's not one of your homework questions, was because they almost always have a final question where they separate. And when they separate, it's as if they were an elastic collision, because all of the potential energy that was stored goes back into the kinetic energy of the two objects. So we get a kinetic collision out of this, an elastic collision. Alrighty. Something else on homework? Squid, you guys do understand that, right? So
Definitely please try.
you guys just want to make fun of me,
No, I want to see.
knowing I'm already like on the edge.
What are you talking about? You can't even finish saying that sentence. Shut up. That's not even bad. Smiling. I mean, it kind of has a smile. Alright, he's fine.
All right, so there's my squid. It's drifting this way at 0.4 meters per second. Is that that's what I'm given? Well, and it says that the water, I'm not sure what to put here. So there, water is ejected backwards, and the squid goes forwards. So the water is ejected at 2.5 meters per second relative to the squid, which is already moving forwards at 0.4 meters per second. So here, I'm going to give you an alternative way to think of this question. The water's inside the squid. Both of them have a velocity of 0.4 meters per second, right? You could consider that there's the squid, which is 1.5 minus 0.13. That's the mass of the squid, moving at 0.4 meters per second to the right. Plus, there's the water, 0.13, moving at 0.4 meters per second. All right, this is the momentum of the system. After the water is ejected, the squid, 1.5 minus 0.13, is moving at some new velocity. Now, we do need to figure out what the velocity of the water is relative to the ocean floor, which should be 2.5 minus 0.4, or 2.1, but it should be in the negative direction. It's expelled, so negative 2.1. This is how I would set this problem up. No, we're supposed to find the velocity of the squid.
Oh, okay.
So I don't know if this works out to the right answer or not. At least, I don't know if this works out to the answer in the book or not. This works out to the right answer. Do you guys follow what I'm saying? Yeah.
So you made that negative, but it's relative to the squid, it's going the other way.
Unless you squirted it in front of them.